Just to do a recap, uh, we were discussing in the last time we met, we were talking about the bridge joints, and the joint of a particular interest to us was there are various joints, but the most important joint is the one between the superstructure and the substructure. And the joint between substructure and foundation is also of interest, but not in a very general sense, but specifically in certain conditions, it is important and interesting for us. So we will resume uh, understanding what are the things that we can do at the joints related to between the superstructure and substructure. So let me start off with that. Okay, so one of the most important aspect of this joint is a usage of bridge bearings. This part of it is something that we need to understand what kind there are. So in today's thing, we will get introduced to different types of bearings and how do they work, and when do you try to use them, when are they most suitable, and when they do a good job and when they don't do a good job. Okay, so we'll be looking at that aspect. Okay, now uh, what exactly we have, this is the bearings are generally they are arranged between the structural part, superstructure and substructure. This is conceptually given to you as to say, if there is a simply supported beam which we normally represent in our sketch form with a pinned joint and a roller joint, and under the action of the load the roller moves forward and backward, and also it rotates. So we are able to identify uh, two definitive uh, deformation patterns for the superstructure which is under this action. That is, one is the movement, sliding movement, and then other one is the rotation. So essentially these bearings are components between superstructure and substructure which accommodate these displacements and deformation in a fashion that is convenient to us and as per our expectations and behavior of in the deformation category. Okay, so they accommodate the boundary conditions such as considered in the structural analysis. So the choice of bearing and the kind of movement they permit or restrain are important to identify so that you model them as a boundary conditions in your analysis correctly. That's where the most important aspects about understanding the bearings are come. Okay, they obviously, apart from this boundary condition, they also transfer load, because without transferring load from one element like superstructure, substructure, the purpose of the bearing itself would be lost. So to understand what do the bearings do, they transfer loads and they allow for deformations to take place, relative deformation to take place between superstructure and substructure in a predetermined fashion so that you can model them in as boundary conditions in your structural analysis. So if you look at the flow of the subject, we started off with understanding the development of bridges, then we understand the type of loads, classification of loads, and then how they are derived, and then we looked at the bridge components, and from the bridge components, now we are moving to bridge junctions, and in the bridge junction, once we do understand this, then we will go to the next step of modeling and thereafter the analysis part. Okay. So we are flowing in that direction. So, but to do the analysis and modeling correctly, we need to understand what kind of structural elements constitutes the so-called bearings. Okay. Now, bearings are used to accommodate relative movement between superstructure and substructure, and we recap again and again the 16 different load types, the force type of load, dead load, live load, snow. Each one of them have a certain loads as well as deformation and displacement loads like temperature, creep, shrinkage, etc., which we also need to accommodate. The relative movement is caused by all these loads. All these loads cause relative movement between the superstructure and substructure, and they need to be accommodated through this element called the bearing, right? All of them cause. all of them cause relative displacement, right? Now, uh, there are certain nomenclature that we use in when we talk about this relative movement. One is the translational movement. Translational movement means movement along a particular direction, and that can be longitudinal, transverse, and in certain cases vertical. Vertical has been highlighted primarily to say that it is not normally always the case, but under certain circumstances, the vertical displacement or translation also take place. Translation does not necessarily mean in horizontal direction. Okay. Then you have another relative movement which we need to accommodate, which we call the rotational movement. And all rotational movement are about an axis. This is along an axis. This is about an axis. So we have a transverse axis, we have a longitudinal axis, and we have a vertical axis. Again, very rarely do we find a situation where we would allow our bridge deck to undergo rotation about the vertical axis, though rotation about the longitudinal and transverse axis is quite common. Then, obviously, after all this, there's a combination. It is not that they are in isolation. Then you have rotational come translational behavior in certain cases, which certain load cause both these effects. So therefore, you need to be careful about accommodating the translation and rotation. Right. Please understand that these are relative movement in isolation, and obviously, for most of the cases, we end up having a phenomena that is a combination of both the translation and rotational movements. Now, how do we get these movements? How do we get this relative movement? It's a simple one. We get it from analysis. Now, remember, the analysis is correct if your boundary condition is right, and you need to design the boundary condition, you need to do the analysis. So there's a interrelationship between them. Therefore, you need to understand the bearings a little better. So essentially what you see here in a model like this, wherein you have a pinned joint and a roller joint. So what do you see? This bearing, whatever is this taking care of this joint, will accommodate rotation only. And this type of joint will accommodate a rotation definitely and plus translation. So when you choose a bearing, it depends upon the kind of behavior you expect or the behavior you want. Both are possible. In certain circumstances, you will control the behavior. In certain circumstances, behavior will happen and you accommodate it. So you decide upon that, and depending upon that, you choose the type of bearings. Okay. Now, as you can see in the case of a pinned joint, you have a bearing with relative motion. Now, I have introduced this sketch now for the first time to you. One day we will go through and look at the uh, answers that you have all submitted for the tutorial number 1, where you were asked to draw up the deformed or displaced shapes. Then we will see where you were right and where you were wrong. Of course, we will do it anonymously. We will not call out name, but we'll share. One day we will discuss the answers presented by you in your tutorial submissions. But if you notice that you can have this kind of a displacement mechanism at pinned end, wherein you have an arrangement wherein the superstructure undergoes displacement towards the left due to the rotation. And of course, rotation is easily understandable, but understanding the fact that there can be a displacement towards the left depends upon your understanding of the behavior and modeling. We will come to that a little later. And on the free end, you will be very able to easily understand, appreciate the reason for the horizontal displacement. You've got so many different load conditions. One of them can cause this. And when you have a rotation will have obviously the angular portion, there is no problem. But an accompanied translation part is something that you'll have to visualize and understand under what circumstances this will happen. And if this happens, what is your boundary condition? If this doesn't happen, what is your boundary condition? Okay, so those are the things that we need to understand properly when we talk about displacement and at the junction, at the joint between superstructure and substructure. Now, there are different types of bearings which take care of different effects. Okay, so there are types of bearing which are classified based on the kind of force action that we can undertake. For example, there are bearings called a rocker bearing, there are bearings called roller bearings, and there are bearings called pin bearing or a slider bearing or a guide bearing. So they are based on the kind of actions, force actions. That actions, remember, in technical terms, every time you talk about actions, you generally are talking in terms of forces. So depending upon the kind of forces they transmit at the joint, they are classified like that. Apart from this, these forces, they can also take care of rotation, sometimes rotation only, sometimes rotation plus translation. Okay, so they are, some of them are classified based on action. And then there are special type of bearings which are generally a combination of all these activities, action as well as displacement simultaneously, and not specifically related to any type of, they are elastomeric bearing, steel plate bearing, curved and pot and disc bearings. These are, we'll see what each one of them looks like or kind of functionalities that they all have. Okay. Now, so bearings can also be classified on the basis of the materials that are going into the components of the bearing. The most easy to understand is the traditional steel bearing, though you may not see this often nowadays. But in some of the older bridges, you can see the steel bearings. This essentially is like a rocker bearing, which will allows for rotation but no translation. Or you have something called a knuckle bearing, in which the rotation is taking place, translation is not permitted. Rotation is taking place across a convex surface and a concave surface. So they call the steel knuckle type of bearing. And there are these which are called the elastomeric bearing, which are basically rubber. And in order to accommodate some sliding between the superstructure, they can also be attached with PTFE sheets. I hope you recall we talked about the materials. The PTFE was introduced at that time, polytetrafluoroethylene, because it has a very low friction. Then you have bearings. The picture you have got here is really not a pot and PTFE bearing. It is actually what is called a spherical bearing. Later on, I will show you what a pot and PTFE bearing, but functionally they are similar. And in spherical bearing, basically you have a part of a concave sphere on which sits a convex sphere, and this convex sphere which is attached to the top and the concave which is fixed to the bottom, they are separated by a PTFE layer so that the rotation takes place with minimum friction. And then if this bearing has to accommodate longitudinal movement, then the top convex surface is also separated from the top plate by means of a intermediate PTFE layer, something akin to this, and then the sliding surface on which is typically a stainless steel. We will see a little bit detail in the subsequent slides. So these are classifications of bearings on the materials, that is steel bearing, knuckle bearing, elastomeric bearing, pot and PTFE, or spherical bearings. Okay. Now, rocker and roller bearings, they were the old traditional bearings, very, very old traditional. Today, you don't see them. Today, hardly anybody makes or uses them, but you should be aware of it, because there are many lot of old bridges on which you will be maybe getting a chance to work on or go and see, or such as rectification, modification, or troubleshoot problem for. So you should be able to understand what a rocker and the roller bearing, and they're usually made of steel, and they work in one direction at a time only. They are not capable of sustaining bidirectional displacement. We'll come to understand, if you recall the previous one, uh, 2 lessons back, when we talked about the breathing unit, you realize that wide decks or most decks have a movement or displacement in both directions. And these bearings are incapable of accommodating movements in two directions. They are capable of accommodating movements only in one direction. So therefore, there are certain restraints imposed by these bearings that you as a designer should recognize and incorporate them in your model. Okay. And they generally restrain, they allow movement in one direction or deformation in one direction and are restrained in the other direction. One example of it, what you can see is a very classical rocker bearing. Basically, you have a bottom in which there is a sleeve. It's a half rotation, you can see, and there's a roller pin on which the top surface sits, and it rotates. And when there is sliding takes place, this curved surface locks with this, and this curved surface locks with this, so preventing displacement in the direction of the traffic. So it only accommodates rotation. This is classically called the rocker because, as you can visualize, it only allows the deck to rock about a fulcrum line. That is why it was called the rocker bearing. This is a very traditional bearing. Nowadays, you will not see much of these. Then you have a concept called a traditional roller bearing and roller bearing with a single roller. This is a classical example. Basically, you have a steel plate at the bottom, steel plate at the top. In between them, there is a roller. When this movement, to and fro movement takes place, the relative displacement between superstructure and substructure is accomplished by allowing this roller to roll on top of the plate. Now, they also suffer from certain defects in the long term. They require significant maintenance, and if you don't do it, quite a lot of them stop functioning properly. And therefore, if they stop functioning properly, your assumed boundary condition becomes meaningless. So much theoretical assumption. Okay. So these are the traditional rocker and roller one. Then what you saw here was a traditional roller with a single roller. Then you also have a lot of examples of a traditional roller with multiple rollers. Now you can ask, what's the difference between single roller and multiple roller? If you understand that the bearing stresses between the plate and a roller has also got a certain limit. You can't say that one roller will take 500 tons, 1000 tons, 2000 tons of vertical load. No. So when that happens, when the load becomes heavier and heavier and the material properties are constrained by the choice of steel that you use, you may end up having to use multiple contact points so that you have a roller which has multiple rollers which are connected by a thing and they are greased and this is fixed to the top. So the rolling takes place and the load transfer is over a series of rollers rather than one single. So this is where the longitudinal movement takes place, and this is where the rotation in this pin is where the rotation is uh, permitted or accommodated. So this is a traditional roller bearing with multiple rollers. Okay. Then you also have different kind of roller bearings which have prevent these rollers from free sliding. So they have grooves and you see them in old steel bridges, but many of these bearings you may not be able to see in India because uh, we don't have too much of steel construction. Now, uh, you have a situation wherein if you see something like that, don't assume that it is a rocker bearing. It is also a roller because the rollers are all hidden inside a box filled with grease to protect them from external damage, corrosion, etc. So they are quite often these rollers are box inside one thing which are filled with grease so that the lubrication, reduce friction, etc. are there. Sometimes these rollers also are not full rollers, they are partial rollers. So that also is a possibility that is used only when you know that the amount of movement is going to be small. Okay. So where do you use these rocker and roller? Mostly used for steel girders. They can carry large loads. They require, but because of their arrangement and the size, they require higher clearances. That means from the top of pier cap to the bottom of the girder, you need a significant height to accommodate these bearings. All of them are metallic in nature, so corrosion is an issue that needs to be handled. all of them being mechanical component also require periodic inspection and therefore also have a high maintenance cost. So these are the pluses, large load, and all of them are negative. They're also quite heavy to handle. Okay, so these have slowly been phased out, and you end up uh, using little more modern bearings, and in which we move to the next type, which is called the elastomeric bearings. And quite often, these elastomeric bearings comes with steel plates. How do you make the steel plate? Basically, you can see this is a bearing. This is how it looks after baking, but it has been for illustrative purposes. The same thing has been split to show you that there is a layer of rubber, then there is a steel reinforcement, the next layer of rubber, then steel reinforcement, then next layer of rubber, then steel reinforcement, then next layer of rubber, steel reinforcement, and rubber. And all they are never individual pieces like that. This is only for illustration to you that has been shown. They actually put inside a casing and baked together, so they get bonded together. And when they are bonded, they look like this, generally black, and they have a top and bottom plate on which to seat them. Okay, and they have sometimes these projections on the side to prepare them, to give them rotational ability but no displacement ability, because this pin will lock into it. So you can, with elastomeric bearing, also create boundary conditions within the bearing design and detailing that will permit controlled movements, controlled deformation, control in one, free in other, control in both, free in both. All these possibilities exist purely depending upon how you detail the top and bottom plates. To get an idea of it, sometimes you'd have a look at IRC 83 Part 2 on elastomeric bearing. You will see all the latest arrangement that are possible and permitted in the code. But this is to tell you, essentially they all look with the rubber materials with steel plates sandwiched between the rubber. Now, elastomeric bearing material is elastomer. Elastomer is nothing but an artificial rubber. You can also use vulcanized rubber. Natural rubber is also possible to be used, but then the variability in the quality of the natural rubber has to be addressed in terms of chemical management. Now, synthetic material is what you have heard of. You would have heard of the term called neoprene or chloroprene rubber. These are synthetic rubbers, and they are generally in the form of granules and powders, and under heat they become transformed into the what you call as the baking or vulcanizing process. They become hardened and become black in color. And what do? They accommodate both rotations and displacement. These are accommodated by the rotations are accommodated by the compressing of the layer. What you are seeing here is essentially the individual rubber layers compressed, so they are all bulging out, and therefore it tells you it's like a proof of the presence of load on the elastomeric bearing. Quite often you might get alarm calls from people saying that the rubber bearings are bulging. Yes, if the rubber bearings are properly loaded, they will bulge. More importantly, the bulging will be uniform from one end to the other. That tells you that there's a good seating. And if you see, the transverse displacement is taken care of by the shearing of the layers. You can see that this bearing is moved in this direction, that this shear, and this bearing is rotated this way, so that you have the slope also adjusted, and that rotation is accommodated by differential compression of bearings here and here. So an elastomeric bearing, how does it differ from the rocker and roller bearing? It can accommodate translation and rotation in both directions simultaneously. And in this instance, what you can see is that it is fixed at the bottom, and this is free to move in both direction, forward and backward. So this type of bearing, the so-called elastomeric bearing, they are made of elastomer, which can be either natural rubber or synthetic material like chloroprene. Both are possible, but both are okay. And both of them are permitted according to our IRC 83. Okay. Now, looking back at the natural rubber, it has certain shortcomings. It is what is weathering resistance? Can anybody describe what is weathering resistance? Yes, what's weathering resistance? Okay, anything else? What about others? They're there today or they are not there? I think I should ask you all to type in your answers in the chat box. That would be easier, and I can see whether anybody is responding. Yeah. What about the others? I think I should then call out the name. Shreya?
Sir, I also think that the wear and tear due to the environmental conditions.
Wear and tear. Now I want you to be careful. Wear and tear requires a physical action, like rubbing, abrasion, and things like that. In this case, there is no wear and tear. There is damage, yes. That is why I want you to be very clear when you understand the definition. When you use the word weathering, don't use it in terms of the way you look at wearing course. Wearing course will undergo wear and tear. Wearing with course will not undergo weathering action. You understand the discussion. What Sukulyan is correct, basically exposure to it. Corrosion, for example. Would you call corrosion a wear and tear?
No.
That's what I want. You be very clear about the terminology. When you talk about weathering, it is a natural degradation of the material properties due to natural weathering action. Weathering means automatically weather is involved. Wear and tear. When do you use the word wear and tear? Nayana, those who have not spoken. Nayana, Bhavdarni.
So weathering means
Weathering we
due
understood.
to wear
We
and tear.
said when do you use wear and tear?
When there is any physical action on it, sir.
Absolutely. There has to be an application of a force of some kind. Okay. So be careful about the choice of the word when you use weathering and wear and tear. All right. So it has only moderate weathering resistance. It is inflammable. It means natural rubber can burn. Burn. When I say artificial rubber, it also burn because after all, that's also what they call it, petro product, end product of a petroleum process. But it is less inflammable. Okay, and the natural rubber is vulnerable to attacks by oxygen, ozone, oils, and fuel. They degrade the material faster if they get exposed to these. Now, uh, do you think there can be any rubber that will be not exposed to oxygen? Is it possible?
No, sir.
No, because atmosphere contains 21% oxygen. So any rubber bearing which we use will always be exposed to oxygen and therefore an oxidation process will start. Now, when you talk about elastomer, which is an artificial rubber, it has got good weathering resistance. This comes out of the kind of polymer chains that we use, that is man-made. Natural rubber automatically whatever the rubber plant or rubber tree gives out, it is. But what is happening is, just like you would have heard about additives to bitumen to make change its properties, today it is also possible to add additives to natural rubber to improve its weathering resistance, reduce its inflammable characteristic. Okay, and elastomer, on the other hand, the material, it's a man-made material, so it is got a relatively, it's not an absolute flame resistant, it is relatively flame resistance. And they also add these antioxidants and anti-oleonants, which prevent increase its resistance to oxidation by atmospheric oxygen and ozone. Actually, this is uh, uh, when you compare the difference, it is quite possible to improve the natural rubber also by the same antioxidants and anti-oleonants addition to improve this property. So today what is happening is the elastomeric bearings that you are getting, you get both. You have quite often in your profession, you'll have a choice. Somebody will come back and say, can I use elastomeric bearings made of natural rubber? Code doesn't prohibit it. All you require to make sure is they satisfy this requirement. That is, they have good weather resistance and they are good resistance to oxygen so that their life is longer. Okay, so that the distinction that you see here is theoretical. Quite often you can manage natural rubber to also get the advantages of a artificial elastomeric rubber bearing. Okay, now elastomeric rubber bearing, how does the behavior, structural behavior take place? Under vertical load, the whole thing compresses and you have a bulging. Okay. Under horizontal load, VH, it shears like this. And if you have a vertical load, it also compresses simultaneously. And if you have a vertical load with an eccentricity, which is equivalent to a moment, then there is a differential compression of this thing and the rotation is attached. Now, this is where, if you notice in this drawing, in this sketch, there's a small uplift has been shown. If you are designing elastomeric bearing code, now we'll not go to the design of the elastomeric bearing now, but in general, our code makes sure that this condition is not created. That means no uplift of any part of the bearing is acceptable according to their code. Therefore, the sizing should be such that there must be a minimum compression from even the worst rotation. There must be minimum compression on both ends of the bearing relative to the compression or angular direction. Okay, so this is how the load deflection behavior is there for elastomeric, for vertical load, for shear, and for rotation. Now, the elastomeric bearings nowadays, you do get natural rubber, as I mentioned to you earlier. Nowadays, most of them are through synthetic rubber. They are flexible in shear, but they are stiff against volumetric change. What does it mean? Its compression modulus is very high compared to its shear modulus. That means it compresses less. That means this so-called vertical deformation is not as much as the stiffness related to this VH. That is what exactly it means. It is stiff against volumetric change, but it is very flexible in terms of shear. And it accommodates to deformation of the individual pads and the cumulative. And what you see on the right hand side is an example of an elastomeric bearing seated under the bridge girder. Now, the reinforcement layer in between them, you introduce them so that as you have seen in these examples, I'll go back to this example. If imagine, for example, if you had not put the steel reinforcement, then what would have happened is, under the same load, this would have bulged a lot more. And when it bulges that much strain, then what happens is the rubber starts cracking. So that means you're not actually exceeding the compressive capacity of the bearing, but because the geometric shape will distort so much that it will start undergoing tearing of the rubber. So in order to use it for higher to the upper limit of its compressive load capacity, we introduce what is called as a reinforcement plates. As you can see here, the reinforcement plates are introduced. They are either of steel or fiberglass, but most of the time in India, most of our bearings are in steel. Very rarely you get fiberglass, and it prevents it from bulging under high loads, and it allows us to resist higher loads. As I told you, that bulging will cause the tear of the rubber if it is too large. And therefore, by controlling the amount of bulging between the layers with the reinforcement, then you allow for the same rubber plan area to sustain bigger loads. That is how the advantage comes out of using what is called as a reinforced elastomeric bearing. Now, because nowadays we also use these elastomeric bearings for resisting the lateral loads due to earthquake. So you have a special type of bearing with steel plates at top and bottom to fix it, and a lead plug. A lead plug provides it the stiffness to limit the deformation and also to limit the number of oscillations the bridge deck goes through before it comes to rest after a seismic event, because of the what do you call it, the property of this lead plug, which is what you call it as lot more softer metal than steel, and therefore it is a lot more malleable. It can change shape very easily. It is a core is placed on that, okay, inside the rubber bearing, and this is a type of bearing which generally used when you are doing what is called as a seismic isolation. That means you want to uh, accommodate the relative displacement between the superstructure and the substructure through a bearing which displaces less but at the same time disperses more energy. We'll understand those principles little later when we come to look at the aspects of seismic analysis and design. Okay, what are the advantages of this? The elastomeric bearings are low initial cost, practically no maintenance. It has got no moving parts that freeze, corrode, or deteriorate, and they are much smaller in thickness when compared to your traditional rocker roller bearing. Traditional, okay. So therefore, what happens is for small spans, it helps in lowering the what they call it height, so that it approach cost reduces by the. It's not a very big amount, but nevertheless for small bridge length, it makes a difference. Now, it is very easy to install and replace. Elastomeric bearings are very easy to install and replace. And what you see is an example here of an elastomeric bearing with anchor studs, which means it is transferring certain type of horizontal forces with restricted movement and allows movement. Say, for example, this is a classic example of what you would call as a guided elastomeric bearing. That means it will allow longitudinal movement, but in the transverse direction, it will not allow movement. That kind of an arrangement you have, or a more classical elastomeric bearing in which uh, it allows rotation and movement in all directions. Now, the hysteretic steel bearing this is where the example comes with the elastomeric bearing with reinforcement and the lead core, or the lead rubber bearing is also called. For normal loads, the transfer of vertical horizontal, it very easily accommodates that, and it accommodates the relative translation just like any bearing. But in addition to the presence of the lead core, what it does is during strong earthquake, it increases the energy absorption. So uh, let us recap. What kind of load is earthquake loading? Adharni, what kind of loading is earthquake loading? Yes, Adharni? Freya? Yeah, Adharni, what kind of loading is earthquake loading? You started to answer, so
It's related to movement, so
no, don't start with the definition. Now you have very clear.
oh,
There is a force load and a displacement load. So what
displacement
kind?
loading.
So don't forget that old lesson. So it's a displacement loading. So in the displacement loading, what happens to the structure? There's a relative displacement between structure and the ground. What does it mean? That there is a energy that is absorbed by the superstructure due to the fact that there's a relative displacement between superstructure and substructure. And that energy, after the earthquake is over, the superstructure shakes on top of a substructure or bearing, and in every cycle of displacement, some amount of energy is dissipated. So the advantage of the lead core bearing is it does higher energy absorption than a pure rubber bearing. That is why in earthquake condition, it is quite often preferred to have elastomeric bearing with lead plug. And how does it work? In every isolation, if you recall the hysteresis diagram, goes linear, then under the reverse cycle it goes, and then next cycle it reduces. Each cycle, the area inside this force displacement graph is the amount of energy that is dissipated in each cycle. So over 4 or 5 cycles, the total energy is dissipated fully, and therefore the seismic action is managed with uh, lower design force on the rest of the component. That is how this hysteretic steel bearing uh, gives an advantage. It absorbs high energy due to the yielding of the lead plug. Okay, at some time or other, you must remember that every time you displace something, you are actually doing work. Going back to your 10th standard physics, force into displacement is the work done. So every time there's a displacement on a structure, there's a force applied to it, and that force into displacement is the amount of energy that gets absorbed, and that energy has to be distributed. Or the other way around, the ground shaking transmits the energy, and how much energy does the structure absorb without deformation or without failure, sorry, not without failure. And that is where all these energy absorption display arrangements are come into the picture, and hysteretic steel bearing is one such uh, arrangement of bearing which allows you high energy absorption due to the yielding of the lead core, not with anything happening to the rubber, but yielding of the lead core. Now, yeah, yeah, sometime depends upon the intensity. See, please remember one thing. When do you need the steel core to yield? You need it in very high earthquake. Then you have much higher energy absorption, therefore much higher energy dissipation. So when you have that kind of an earthquake, you ask the question after every earthquake. I said no. After most normal earthquake, the behavior will still be within the elastic range. But in the high earthquake, the very, very high earthquake zone, earthquake events, then the yielding will take place. And at that time, yes, the lead core will be permanently deformed, and then you will have to replace it. You understood? It is not necessary that every earthquake, at the end of every earthquake, you need to replace the lead rubber bearing. No, it is only when the theoretically the design earthquake comes in. And since earthquake being a natural phenomenon, you cannot predict that every earthquake will be of the same magnitude. Okay. Now, when you are using elastomeric bearing and you want it to have a sliding capacity, normal elastomeric bearing, let me show you the normal elastomeric bearing. This bearing does not allow for relative displacement, translation between superstructure and substructure, because this rubber is bonded to this steel plate and this steel plate is bolted to the top. But if you want the bearing to allow the displacement, then what you do is you end up putting a PTFE sheet to be pasted, and on top of it, the top plate has a stainless steel backing which will slide on it. So then in that case, this type of elastomeric bearing will practically transmit only vertical load and rotation. There will be hardly any sliding on it, because between the PTFE and the stainless steel, the free sliding will take place. Whatever is the frictional load, that will be the only thing come. Why do you need to use that? You can use that for a simple reason. When you do that, the as I've told you earlier, the shear capacity displacement is large, but the shear capacity, larger shear displacement requires larger rubber. Volumetric changes are very small. So if you are transmitting only practically vertical load, then the thickness of the whole bearing can be reduced a lot. But obviously, if you end up having one end sliding, the other one has to take all the longitudinal forces. So you need another mechanism there. So typically in all these things, there is no free meal, as they say. You take an advantage in one place, you tend to pay a price in the other places. Okay. Now, similarly, when you have an elastomeric bearing with movement restriction, here it was a PTFE which allows movement in both direction, but you can have same elastomeric bearing with restraint. What does this arrangement tell you? It tells you that the superstructure is free to slide in this direction, but is restrained from sliding in this direction. Why? Because the bottom plate abuts against the top plate at this location, preventing translation in this direction. So you can engineer solutions with elastomeric bearing which mimic unidirectional movement, bidirectional movement, omnidirectional movement. All that is possible. It's only a matter of how you detail the bearing top and bottom plate. That's all. For example, another guided elastomeric bearing example is you have an elastomeric bearing potent PTFE sheet with a embedded guide, and this top plate with stainless steel sits on it. So what does it do? In this direction, no relative movement between superstructure and substructure. In this direction, free movement. Rotation in both directions is still permitted, right? So these are ways in different types of elastomeric bearing that now each one of them lead to a certain boundary condition, which you must remember when you choose the type of bearing when you're doing your modeling, so that the boundary condition connection between superstructure and substructure is designed with the relevant degrees of freedom as you decided properly input. Okay, this is going back to the repeat there. You saw only the PTFE sheet. Now this is a PTFE sheet with the siding stainless on top plates. This will permit movement in both directions. Now, this is nothing unique to this. Stainless steel and PTFE is a common theme you will find in all the bearings, whether it is potent PTFE or elastomeric bearing, where you want the relative movement, or even spherical bearing where you want the relative movement to take place between the superstructure and substructure. Okay, it is used in combination with elastomeric bearing because you can accommodate rotation also in that. That allows for the freedom of the superstructure from being subjected to unnecessary restraint forces. Right. The advantage of pot PTFE, PTFE, is that it is non-stick. It has got very low friction, and therefore this is the most commonly used material in bearings where we want sliding to take place. Why do we want sliding to take place? Because we don't want restraint to free movement. Why do we not want restraint to free movement? Because all restraint lead to forces, as we have seen last time when we were talking about the bridge breathing units, not the bridge vibration unit. When we talked about the bridge breathing unit, if you don't allow the breathing to take place, forces will appear, which will affect both the superstructure and substructure, and of course the connection element, whatever we are using. Okay. Typically, you have these three types of bearing. This is restraint against translation in both direction when you have this restraint both ways. This generally represent translation restriction in, say, this direction and freedom in the other direction. This indicates it's free to slide in both directions. These are all indicative things that you must be very carefully aware to choose. Now we move to the next type of bearing, which is pot bearing. Now, typically arrangement of the pot bearing, how does it look like? You have a base pot. You think of the pot as nothing but a hollow cylinder. Inside that hollow cylinder, you have this gray colored material is the elastomeric disc. It's nothing but an elastomeric disc. And at the end of the elastomeric disc, you have a sealing ring, a brass or a stainless steel sealing ring. And on top of the sealing ring, you sit what is called as a piston. It sits on top of it. And this whole mechanism is below this, and between the piston and this, there's a predetermined gap. And on top of this piston, if you want a sliding behavior, you introduce this PTFE. But if you don't want the sliding behavior in what we call as the pure pot bearing, then this sliding bearing, this PTFE layer goes away, this stainless steel goes away, and this backing plate is solidly connected to the piston. That's all. The movement surface is eliminated, and that becomes a pure pot bearing. But this photograph is actually for POTCUM PTFE bearing. But remember the load transfer mechanism. You always have the vertical load transmitted through this piston to the elastomeric disc, from the elastomeric disc to the base plate, and from the base plate to the pedestal onwards. Okay. So What are the pot bearing? The steel container or pot with elastomeric bearing, they resist really, really large load. Now you will ask, the vertical load is being transmitted by elastomeric disc here. Vertical load is also transmitted through this elastomeric pair. Then what is the difference between them? Between this behavior of this elastomeric disc and the pure elastomeric bearing. Is there a difference? Let me ask. Is there a difference, Shreya? Yes, please. Is there a difference in the behavior of the elastomer in a pure elastomeric bearing or the elastomer which is in the pot and PTFE bearing? Yes, Naina, you never had a chance to open or say anything today. Is there a difference?
I think sliding is restricted in this, sir. Pot PTFE.
No. I asked in the behavior of the there is a pure elastomeric bearing which I showed the first photograph, and in the pot and PTFE also there is an elastomeric disc. Between this elastomeric disc and that elastomer for the elastomeric bearing, is there a difference in behavior? Structural behavior. We are not talking about anything else. Movement is a different issue. As I told you, that is not handled in the elastomeric disc. So is there any behavioral difference?
Sir, in the elastomeric bearings, there is a reinforcing plates.
Okay. In this there is no. Okay. But
Yes.
what difference does it do to the structural behavior? Or there is no difference at all? Both are same. That is a different matter. High load is, why is there high load? After all, I can design any bearing for any load. It's only a matter of getting an appropriate size. Yes. Any difference in behavior? I'm talking structural behavior of the elastomer. I'm not talking about movement or anything like that. We'll come to that a little later. Cannot think of it. Okay, let's go back to the picture. If you see this elastomeric bearing, this elastomer is open to air. You agree? Or more importantly, let us take a look at a really installed bearing photograph. Yeah, this. You see this elastomer is open to air? Yes or no?
Yes, sir.
Okay.
Yeah.
Now you tell me, this elastomeric disc, once it goes into the pot and it is covered by this piston, is it open to air?
No, sir.
No.
So what difference does it make? Does it make any difference?
Exposure
the
to
exposure?
the
No, again, you're yes, it is not exposed to air, agreed. But what difference does it make structurally? There's a word for it which should come to your mind.
Restrained.
Restraint is not the correct word. And you're going in that right direction. But if a
Restraint to
material is
sliding?
surrounded on all sides by another material, what will you call the first material as? It is a
Confined.
it's a confined material. So if the elastomer is open, unconfined, and the elastomer is confined, what will be the difference in behavior? I think you have forgotten all my old classes. You had the similar difference when you saw confined concrete, unconfined concrete properties I introduced confined concrete properties. What did you see the difference? Forgot. Yes, please. What's the difference? What will confinement do? Again, I want you to be clear in your language. I can increase the load carrying capacity by increasing the size. So what does confinement do?
Increase ductility. Ductility in concrete.
You're gone in one direction, but you're leaving out the more essential part. Okay, you recall the graph. You remember for concrete, I showed you different models, including one Manders model, which is most popularly adopted. And we talked about sigma Cu in the two cases. You recall that?
Yes, sir. Strain is less in unconfined.
Strain in ultimate strain is less in unconfined. Language, clarity. Which condition has more ultimate strain, confined or unconfined?
Unconfined.
Confined is having the more.
Sorry, confined.
Which one has the higher yield strength, confined or unconfined?
Confined.
Confined. So in both the cases, confinement leads to increased ductility. That is, you caught on that because you said the ultimate strain to yield strain increases. Yes, no doubt about it. Confinement also increases the ultimate strength. So same thing happens with elastomeric bearing. Same thing happens with any material which has got a tendency to have a large Poisson's effect. Rubber, you agree it has a very large Poisson's effect? Remember we talked about the material. Poisson's ratio for rubber is what?
0.5.
0.5. Poisson's ratio. So what does it mean? If I apply the vertical load, it will tend to deform in a perpendicular direction. Correct?
Yes, sir.
So therefore, when it is unconfined, the permissible stress in the rubber is of the order of about 20 MPa. I'm giving approximate value. And the same rubber, if it is used in pot bearing, where it is confined on the sides by the walls of the pot, at the bottom by the pot base, and at the top by the piston, then the vertical load, the bearing stress on the rubber will increase to 40 MPa. Same rubber, same grade. Okay. So that is how you carry the larger load, Sukalyan, not because just larger load is not. For a smaller bearing size, for smaller elastomeric disc size, you will be able to carry larger load because the compressive stress permitted on this rubber due to confinement is much higher. You should be very clear about why the larger load. Otherwise I can, if I have an X size bearing, I make double X. My area becomes for a square bearing, my area becomes 4 times. I can say I'm taking 4 times load, but you're also consuming 4 times more material, right? There's no fun in that. So pot and PTFE, the elastomeric disc, because it is confined, carries larger load. That is why this says they use the word it can carry larger load for smaller size of bearing. That is what is more important. Okay. It resists larger loads than the, when they mean elastomeric bearing, they mean the unconfined elastomeric bearing. Okay. The rotation is accommodated by a deformed elastomer. Here also, if you go back to it, the top and bottom, the rotation is accommodated by differential compression of this confined elastomer. We have a third type of bearing which has come about, which is called the curved spherical bearing. So you saw the elastomeric bearing, you have a patent PTFE bearing, then you have a third type of bearing called the spherical bearing. So how does the spherical bearing work? From outside, it looks like patent PTFE. If you take a look at this, and you take it, they look similar, but they are not the same. So here what happens is they create a concave spherical surface here on this metal, and they create a convex spherical surface on this, and on the back of that convex, okay, this is inside this only, you can see this line is the concave circle, and this is the convex circle. So that is why it got the name spherical bearing. It can accommodate rotation in both direction by the relative rotation of the two sphere. Okay, that is how it rotates. And then the sliding can be created on tops are spherical. You attach a PTFE and a stainless steel backing plate, and you have the translation. The rotation is accommodated to any axis. Okay, and in spherical can occur to both axes, and slider surface in Teflon coated so that you allow translation. This also takes larger loads. It also takes very large load. Why? Because basically you're talking about the bearing stress between steel and PTFE, this curved PTFE, and that curved PTFE and steel. So basically the PTFE permissible bearing stress is very high, and because it's also confined within this, it automatically also achieves a higher bearing stresses than exposed PTFE, right? So this also is used for a very large, what do you call it, loads. Now, I have a question of interest, which is from the point of view of practical use. Which of these three bearings is most forgiving from the point of view of bad workmanship? Bearings generally fail due to bad workmanship. Now, which of these bearings do you think are most forgiving when it comes to bad workmanship? You understand the question? When you use this bearing, which requires the most perfection and which requires the least perfection? Anybody wants to attempt it now? To make a full sentence. The least skill. I'm not saying it doesn't require. You can't willy-nilly lay an elastomer. It requires it. If you make small mistakes, it is. But why? Why do you say that? What's the problem with the uh, other bearing? So okay, one of these days I will.
Misplacement of this the misplacement of this concave plate and convex plate, if it is missed, or the layers if they are missing anything,
You
then
can't
it is
open it.
it is
Naina, when you use in the
problem.
site, you cannot separate out the thing. It comes as a single unit, the top and bottom, and you just install it, and it comes with erection clamps, erection bolts. You remove it after you are placed and grouted. But that is still not the main reason why elastomeric bearings require. You don't assemble anything at site. Whether elastomeric bearing also comes from factory as to use. Patent PTFE also comes from factory as to use. You don't assemble them at site at all. If you're thinking in that term, forget about it.
Due to misplacement,
What misplacement?
instead of fixed location, we are going with some other bearings and
error.
the
That is
direction.
error. That is error. That is like telling if I change my fixed end and free end, it'll make a difference everywhere. That is not the question. That I'm not talking in that sense. Okay, basically to understand that you have to understand the load transfer mechanism, right? So let's take a look at this bearing. This bearing. This bearing is easy to understand, right? There's a load here and there is a flexible material here. If this base is even if it is not properly grouted, there is enough flexibility into it to accommodate the vertical load. Okay, this base is not grouted. But what happens in the case of a potted PTFE bearing is this load from the whole thing works. We have assumed that the potted PTFE works for higher load. Why? Because of the confinement of the elastomeric disc. What does confinement mean? In physical terms, just having material all around is not confinement. Under load, certain behavior must be ensured, right? You are arguing, we argued, and rather we justified the higher load by saying there's a confinement of this piston, there's a confinement of the base, and there's confinement at the top. As far as the element level, there's confinement. But how does the confinement at the base really work? Practically speaking, how does the confinement, see, the load is transferred from the piston to the elastomeric disc, from the elastomeric disc to the base. From base, where does it go? From the base, where does the load go? Pedestal. Okay. So the pedestal will supply the reaction. Under what circumstances can the pedestal fail to supply reaction? Can it fail to supply reaction ever? Or no, it will always supply reaction?
Sir,
You are describing all qualitative. How do you achieve good contact? Remember, the bearing comes from a factory. Pedestal is cast in situ. So how do you achieve good contact?
the surface of the pedestal has to be properly in contact
No,
with
you
this.
are
the base of, yes.
you're all playing God, let there be light, and there was light. We are human beings. Let there be contact and there was contact. We cannot wish it like that. We have to do something. So what do we have to do? Okay. So if I'll give you a theoretical possibility first, and if the grouting is not done and the contact between the bottom plate of the bearing and the pedestal is not there all over, then what happens?
Load is not transferred properly.
Load transfer will not take place. The load will go to the other places. That means the bearing stresses will be non-uniform and there is a space below the bottom surface. So under the load action, what will happen to the base plate?
Base plate will be damaged, sir.
Don't use the word damage. And nobody is breaking them. If I were to ask you, if I put a truck on top of a bridge deck, what happens to the bridge deck? So what happens in this case? The base plate has got no contact in certain area, but it has got load from the elastomer at the top. So what will happen to the base plate? Base plate will bend. If the base plate bends, is it providing confinement?
No.
So now you come to the crux of the issue. Your confinement will be compromised. And when the confinement is compromised, what happens? The elastomeric bearing deforms. elastomeric disc deforms. In which case, what happens is that the piston tends to come and sit on top of the pot, which is not supposed to do. In which case, what will happen? The rotational capacity will be compromised because the piston edge will start touching the pot edge. Correct? I will show you some other day very poorly installed bearing photographs. I have a lot of them. I will on another day when we talk about ill-placed bearings, especially on that, I will show you that. But for the time being, what it means is if this deforms, this elastomeric test settles, then there's a possibility, depending upon the extent of the absence of ground, there's a possibility that this piston might come and touch the pot edge. And if it touches the pot edge, then what happens? Rotational capacity is gone, correct? Okay, just excuse me. I will show you the, I don't know whether I have a photograph of a, okay, this is, well, just hold on. Let me locate from another source. Let me open the code and I'll show you the assembled image of how a code, a cotton PTFE bearing. Just give me 1 minute's break. I'll join you quickly.
Yes, sir.
Yes, sir.
Yeah. So essentially, this is how the assembled potted PTFE bearing. This is for with guided, but if you want free slide side guide bearing, and this is all. Let's take an example of a simple fixed pot bearing. There's no movement, only rotation. Then what happens is the vertical load comes from here and the vertical load gets transmitted on top of it, which in then turn gets transmitted. And this will remain confined and non-deformable. As you can see, the word confined elastomeric pressure pad will only if this bottom surface does not deform. And to prevent the bottom surface deformation, you need good quality grout. And if, for example, if the grout is missing in this, this will deform. When deform, this elastomeric disc will change shape and occupy the full space. Thereby what happens is this gap will come down. This gap between the piston and the pot will come down. And if it is so badly grouted that this can even come and touch. And when it touches, under any rotation, this will prevent the rotation. So rotational capacity is lost. So therefore, this pot and PTFE bearing requires extremely good quality grout at the base. And of course, top. I'm not denying that, but top is less important because elastomer will not expand. It will only confine. It will, and not only that, because the piston is much thicker than the base, its rotation is very less likely, even if the grout quality is bad. Okay, so that is the reason why you need good quality grouting for this, as opposed to elastomer. Even if the grouting quality at the base is partially done, the elastomer disc will expand slightly. It will have non-uniform pressure. All those will happen, but it will not what they call it, lose its rotational capacity, etc. So that is why elastomeric bearing is what they call it, more forgiving. Now comes the question of the third category, the spherical bearing, right? So why is spherical bearing the most unforgiving? Okay, to understand that, I will again open the spherical bearing code, which is now withdrawn, but it is good enough for our understanding of how this behavior works. locate the sketch in the code. Code I've got. Okay, I think this is any one of these is good enough to explain the point. Okay. So in the case of spherical bearing, can you see my screen? Okay. So basically, if you notice, this is how a spherical bearing, the concave surface is created and the mating concave surface. Now, as you can visualize, the load comes from down through that top. It tries to establish contact over this whole surface. Now, imagine the same situation as potent PTFE bearing. If you don't have grout here, then what will happen? This plate will bend. And if this plate bends, then what happens? This convex surface will not have contact over the full area. Correct? Because that is very rigid. That convex surface is much thicker because it has this thickness plus the backing plate. So that will not bend and follow the geometry of this. So what will happen is the convex surface will be touching this concave surface at selected point, because of the fact that this surface has bent under the first action of loading. Now what happens if it is touching at selected point instead of uniformly everywhere? What will happen? No. See, what will happen? This is where you and I have a different way of explaining things. Is the contact between the convex and concave gone totally, therefore no lateral flow transfer will take place? Or the contact is reduced in area? That's why I'm saying I want all of you to be very clear in expressing yourself. The contact area will reduce, as you can see here. If the contact area reduces because the bottom has deformed and this perfect matching which they had machined and created is not there, contact is reduced, then what happens to the contact pressure?
Increases.
If the contact pressure increases, what happens to the PTFE sliding surface? It will get crushed.
Yes, sir.
If it gets crushed, will it then rotate?
No, sir.
No.
So it will not even rotate. There, depending upon how much deformation takes place, it might still allow some rotational capacity. There's a guideline given in the code how much you can allow and to what extent you can still see the bearing. Here it will stop functioning and you will not even know. You will not know that the rotation is locked until you start seeing other things. That is why the most unforgiving bearing is a spherical bearing. And the most forgiving is a pure elastomeric bearing. This you should remember next time when you choose it. Of course, today spherical bearing code is withdrawn due to various copyright issues. So you can't use them anymore until they reissue this code with another amendment. Okay. So now coming back, we'll go back to our understanding of the bearing itself. Okay. So among the three types of bearing, the spherical bearing requires the maximum accuracy in placement. Potent PTFE little less, not a lot of less, but elastomeric bearing you can be a lot more lax. But I'm not saying anywhere you should be lax, but I'm saying if it happens, you are partly saved. Okay. So now you have a translation come rotational bearing. You have a possibility that the sliding surface is on top or the sliding surface is at the bottom. Both arrangements are possible, but preference is for sliding surface at top because the bottom sliding surface tend to attract dust because gravity, everything comes and settles at the bottom. So once it gets dust, this sliding surface can be damaged easily. So this is not the preferred bearing arrangement. Most of the time, we prefer sliding surface at the top because under gravity action, most of the dust, if it comes, it accumulates at this level far away from the sliding surface. So you have an arrangement wherein you are rotating, allowing unidirectional rotation and sliding here. And you have a spherical type of bearing which allows bidirectional rotation and sliding there. So both of them are possible. Okay, so the rotational bearing, they don't roll off for the simple reason their limitation. They have a limitation in the rotational capacity because these are matching surfaces. So you can find that if it what they call it rotation exceeds their limit, they will start touching. Metallic components will start touching, and this is a system wherein you have a spherical thing on a convex surface, and this is a situation where spherical surface is on a flat surface. This is not common. That is, we don't have a spherical bearing in which the top surface is flat, because then the contact stresses are very high. You need to do a lot of metallurgical treatment to make this hard. So the most common one is convex on convex, which is what most of the spherical bearings that we see in the world are. Okay, it's a good example of a disassembled curved spherical bearings in which you can see the bottom concave surface, the PTFE is lined, and then they are lowering the top convex surface. You can see the size of the bearing is, you can imagine this man will be around 1.6, 1.7, say maybe about 2 meters tall, European. So with his bending, he may be about 1.5, 1.6 meter in this height, and this size is approximately that. So that's a really large capacity bearing that requires handling by this much weight. Okay. Now, when it comes to bearing, what are the primary checks that you must remember? You cannot have rocker in all direction. It's not possible to manufacture. Remember, if rocker means it is allowing rotation. Remember, rocker bearing is different from elastomeric bearing, pod and PT. When you use the word rocker bearing, it allows only unidirectional rotation. So you cannot possibly have rocker in all directions. So be careful about it whenever you use the rocker bearings. All right, it is not possible to manufacture such bearing. And not all roller in all direction. You can again, roller is also possible only in one direction. You cannot have roller in all direction. That doesn't mean, but the question is only, these are the restrictions that you end up having when you use rocker and roller bearing, right? These are overcome by using the other types of bearings, right? So freedom of movement, you have a fully free movement. That means it allows you, sorry, the other way around. This allows you movement in both directions. This allows movement in one direction, and this doesn't allow movement in any direction. That is how you represent with a dot, with an arrow, or the bidirectional arrow. You can choose any one of those for any one of the bearing. That's your choice. Subject to, remember, when we chose about articulation, we talked about the radial, tangential. Keep that all in mind. Combine with this when you choose the type of bearing in your supporting arrangement, right? Now, if you take a look at it, the different kinds of movement that you have, you end up with the millimeter per meter. If you look, the least of them comes with steel, because primarily in steel you have thermal movements are the only thing possible. And in the case of concrete, RCC, when they write concrete, this concrete means reinforced concrete. It is the little higher, because in addition to thermal movements, you end up having in the negative direction something called a shrinkage phenomena. So therefore, you end up having something like 0.3 to 0.3 millimeter per meter expansion to about 0.6 millimeter per meter compression, contraction, sorry, not compression, contraction. I'm also making wrong choice of word. And in case of pre-stress, as far as the expansion is concerned, you primarily have thermal expansion, which is around 0.3. You notice that the thermal expansion is higher in steel because steel tend to heat compared to the atmospheric temperature. Steel tend to absorb heat faster and therefore rise its temperature more, and therefore it has more movement in the expansion direction. But in precess concrete, the contraction direction, the movement is more primarily because apart from shrinkage in the contraction direction and temperature fall, you have an additional phenomena called creep, which happens in precess concrete due to the sustained compression of the precessing cable. So therefore, you have more movement. So when you choose your bearings, you need to take care of it. The expansion side is generally smaller. The contraction side is generally larger. This you have to be careful, except steel. Steel has got both equal. Okay. Now, which type of bearing should be used? So the factors when you consider selecting bearing, you will look at the vertical and horizontal load. You look at the translational rotational movement. You look at the available clearance or the footprints and the height that is available. You look at the environment, corrosion, temperature range, etc. You look at the initial cost. You look at the maintenance cost, and you look at the availability in your region. Taking care of all these things, you will choose what type of bearing to use. Okay. So when you choose some basic guidelines, structural deformations occur under normal load. So there should be no unlimited movement at support. That means what? You must be in a position to control the deformation and support under normal loads. You must be able to. Whether you use the internal resistance of elastomer or whether you use external ones like guides and pins and things like that, that's up to you. Okay. Static analysis should give conservative results. Okay. But you must also consider geometric and kinematical conditions so that you assess the deformation in these bearings correctly. Okay, high value bearing work only if properly installed. What are the highest value bearing? You have the spherical bearing. Bearings require inspection. They also undergo wear and tear. This is where your wear and tear concept, in addition to weathering, will appear in all bearings, because wherever you have a sliding force, there's a friction there, which means that material will slowly deteriorate. And if there are cycles of loading, then also material deteriorate. We'll come to that a little later and we talk about cyclic loading concepts. Okay. Now to tell you some very poor installation of bearing. What I told you about, look, take a look at this. Do you see grout below? This is a project in India. It is commissioned. It's operational. And look at the date of the photograph if you want to see. 2016. I'm not showing you a photograph from very old age. You don't want to know who is the contractor who did this kind of work? Any curiosity? Huh? The largest contractor in the country. Yes. So what does that tell you? It's a concept that I keep telling everybody. You will get the quality that you want. In this instance, I tell the contractor is giving the owner the quality he wants. That means the owner doesn't care what he gets. As long as it's standing, it looks like a bridge, it looks like a bearing, he's okay with it. If you establish that level of quality standards, you will get only such work. You take a look at this. You can see this. The bearing inside the elastomeric disc has deformed so much. The levels are all gone, so that it is gone and this piston is touching the pot. So will it rotate in that direction? Absolutely not. Remember, this is also the same contractor. Okay, I have got a whole lot of photographs. So next time when you go to the sites, please have a look at this. Have a close look at it and see if they have done the right job. If not, tell them the correct way to do. Okay. This is another poor installation of bearings. Can you tell me why this is poor installation? It's an elastomeric, conventional elastomeric bearing, but I call it as a poor installation. So we'll start. Shreya, why is it poor? Are you able to see the slide, or should I magnify it some more?
Sir, is it the alignment?
What alignment? Then I want you to be correct. Alignment is in the direction. What direction
So
problem?
the placement, the
Huh?
placement,
What is
the
placement?
placement.
Is location.
Yeah.
I want you to be correct in your language. What's the problem? Okay. Naina, next your turn. What's wrong with that? Or there's nothing wrong. You can also say take that choice. Can't guess? The photograph I thought was quite
There is
clear.
there's some gap between the bearing and the plate above it, sir.
Ah, okay. And as a consequence, what do you see? So you have noticed the problem that the contact between the superstructure and the bearing is not it's not uniform. Correct?
Uniform. It's not uniform.
So what did it lead to?
It is leading to the deflections of one side. It is more
It is leading to non-uniform loading of the bearing first, always. Okay. Looking at this, how suppose tomorrow I come and grout that gap between, now in this condition I grout the gap between the top plate and the bearing. Will you be happy?
No, sir.
Why? Why? Suppose I had shown you this photograph after sealing that gap. How would you know that this is poorly installed? Will be, there is no future tense, no? The photograph is in front of your eyes. Correct. So what does that tell you? If you see a photograph in which there is no gap, Naina caught on because of the gap. Correct or not?
Yes, sir.
Suppose the gap was sealed by me, and then I showed you the photograph and say, how do you know it's a poorly installed bearing? And what Sukalyan said, you will look for the load transfer behavior. You can notice that the elastomeric is bulging up to approximately here, correct? And there is no bulge here. Agreed or
Yes,
not?
sir. Yes, sir.
Yes.
And if there is no bulging, what does it mean? Now, as a structural engineer, you
That
should
part
talk.
of bearing is not loaded.
Absolutely. So it's a partially loaded bearing. Then what will happen? This part of the bearing is going to fail soon. It is not meeting up the design. Your bulging is like your, you remember that all of you have heard that you need to measure slip in pre-stressing, correct?
Yes, sir.
Why do you want slip? Or you don't want slip at all? You're happy with zero slip in pre-stressing operation.
It will let us know if there's something wrong with the.
No, nothing wrong. You want slip during the pre-stressing operation, or you don't want slip during the pre-stressing operation? First, let me take a call. Okay, Shreya, you want or you don't want?
There should be some.
Okay, so you want. Sukalyan? Naina? You want slip in the pre-stressing operation or not?
I don't know, sir.
You don't want. You don't want, or you
No,
don't
I
know?
don't know. I don't know.
You don't know. Okay, fine. Gaudarni?
No ideas.
No idea. Okay. You want slip. Okay. Now I'll ask the question to those people who said you want slip. Why do you want slip? Shreya? Shreya, why do you want the slip? Don't know? Yes, Shreya. Didn't say anything.
Sir, I'm thinking how to explain.
Okay, Sukalyan. No, 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 no. Okay, I'll put it in simple English. The presence of slip is the proof of existence of tension in the strand. I can have zero slip with zero force in the strand, right?
Yes.
So the presence of slip or observation of slip is a proof of existence of tension in the strand. Because the strand is in tension, therefore it tries to recover its length, shorten it back, and therefore the slip take place. If you recall the precessing arrangement, I think all of you have forgotten that part. Similarly, in elastomeric bearing, this bulging is a presence of load and a lack of bulging is absence of load. You understand? Now the significance of having bulging uniformly all around. Even if I can camouflage, I could have camouflaged this by grouting it after placing the bearing, correct? What does it mean? It means that there is more compressive force here than in this location, which means what? Whatever assumptions you have made for your design of the pier cap, the load positions have all changed. It could be favorable, it could be unfavorable, correct? All right. That's the end of the today's talk. I will close here now and ask all of you to have any questions, or if you can summarize what you have seen today one by one. Wants to take the lead? All of you should be open to speak, at least to me. You don't have to worry. I'm not here going to be very judgmental. I will only want to give you direction to say how to say anything correctly. That's all. You can speak freely. What else? Okay. And after choosing the bearing, what will it lead to? No, that is, I'm not, right now, we are not worried. I just introduced the topic only to familiar with the other aspects of bearing, which is related to construction. But I'm telling from a designer's perspective, after choosing the bearing, what does it lead to? Absolutely. So, to summarize, you have seen at the junction between superstructure and substructure, what are the kinds of relative displacement takes place. For each kind of relative displacement, some of it you can control and choose as you want. Some of it, when you allow it, depending upon what you allow and what you choose to restrict, you choose the type of bearing and the type of arrangement. And then thereafter, once you have chosen the type of bearing, you will take it. There are 6 or 7 criteria I mentioned as to why and how to choose the bearing. And after you have chosen the bearing, you will use that bearing's features to define your boundary conditions in your model to carry out your analysis. Okay. Right. Any other questions for the day from your side? If not, then we'll call it a day today and meet next Friday again. All right. No, 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 not at all. It's no use. It's absolutely wrong concept. I don't know whether what you observed is correct, or maybe they are doing something else which you are not able to understand. That's also a possibility, but nobody will enclose elastomeric bearing in inside steel. Unless you show me a photograph, then maybe I can give you an input. That is possible. Looking as if they're enclosing the, yes, pedestals have weak pedestals have been reinforced by confining with steel plates all around and grouted and filled. That I have seen it done. Okay. So we meet again next week. You please pass on the message to the others that the classes will be more regular from now on. All right.
Okay, sir.
Okay then. Good night, everybody.
Bye, sir.
Thank you,
Good
sir.
night.
Good night.
Good night.
Thank you, sir.